Hey everybody, we're going to look at drawing graphs of waves when they interfere with each other. And so I'm going to show you a couple of tricks and techniques that you can use to better understand what's going to happen when you have two waves which aren't simple boxes that interfere with each other, kind of like you have to do on number 2 of your homework. So the first example I'm going to kind of work through. The first thing I'm going to do is I'm going to kind of give these individual waves a name or a color. I'm going to do one in blue and one in red. So I'm not going to just try to jump into drawing this second graph over here. I'm going to kind of go piece by piece as to what's happening. So notice first of all that you're given the velocity of each wave. Each wave is moving at a velocity of 1 centimeter per second. And then further realize that each of our line on the graph is half a centimeter. So what that tells us is that in 1 second, the blue wave front is going to move forward 2 boxes. And the red wave front will move forward the same 2 boxes. So the blue wave will move forward 1, 2. The second wave will move forward 1, 2. And so after 1 second, the front edges of the waves are going to be interfering with each other. After 1 more second, the front edge of the blue wave will move forward 2 more boxes. The same will be true of the red wave. And so after 2 seconds, the centers of the 2 waves will be overlapped with each other. And that's the time when we want to draw, because we're asked to do this when they completely overlap. And so that's when the 2 wave centers are going to completely overlap with each other after a time of 2 seconds. So pay attention to both the velocity that you're given and the scale in determining when they're going to be completely overlapped. Also notice that they're going to overlap right in between where they started, so along this line right here, which if we count over from the left edge is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines over. So what I'm going to do is I'm just going to transfer the 2 waves to the graph on the right. I'm not going to worry about what they do yet. I'm just going to move them over. And so counting over 10 spaces from the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the position where those 2 waves are going to overlap. And I'm just going to copy the waves over. The blue wave has an amplitude of half a centimeter. So looks like that. And then the rest is just a flat line. And the red wave has an amplitude of 1.5 centimeters. So the red wave would look like that. And then the rest of it would be a flat line. And so once I've kind of transferred where they're going to be overlapping with each other to the other graph, I could erase some of these extra things that I drew. And then it's just a matter of adding up the amplitudes. So the amplitude of the blue wave is 1/2 a centimeter. The amplitude of the red wave is 1.5 centimeters for a total of 2 centimeters. So that means that the resulting wave will have an amplitude of 2 centimeters. So I'm just going to draw me a dot at 2 centimeters. There's no other points on the wave where they do anything different. And so the maximum amplitude is going to be 2 centimeters. Right here and right here, the amplitude will be 0 centimeters. So my resulting wave is just going to look like a triangle of amplitude 2 centimeters. And so I'm going to draw a black line to represent the final wave. And so you can kind of rough draft sketch it out like that using a pencil or something, and then go back and erase anything that you don't want to keep as your final. And then kind of, go back over and fix it kind of sort of like that. And so that's what our resulting wave would look like for number 1. And again, it's going to take 2 seconds for those to overlap. So what I would recommend that you do is do those one at a time. And then as you do each one, check the key just for that one and make sure you've done it correctly before moving on to the next one. Remember, if the wave is down instead of up, that you need to make its amplitude negative. Question number 3 on your homework asks you to kind of think about the same waves. All those pictures are basically the same, but here it's asking you to plot the velocity of a point on the string as a function of time as the 2 waves move through that point. So basically what it's asking you to do is to describe the velocity of just that one point as the waves move through. So if you kind of think about what's going to happen to it, change my coloring there. I'm going to do the same kind of color convention. I'm going to make this wave blue and this wave red. As the blue wave moves through that point on the string, it's going to move up a little bit because the wave goes up at first, and then it's going to move down, and then as this middle portion moves through, the string's not going to go anywhere. And then a similar thing is going to happen for the red wave. The red wave is going to make the point move up as this part moves through, and then as this part moves through point P, the string is going to go back down. And so over here, we're going to have something where we have a positive velocity. Don't start drawing this yet. And then a negative velocity. Then it's going to be 0 velocity for a while. And then we're going to have a different positive and a different negative velocity as the red wave moves through. So we now have to figure out 2 things. Number 1, what those velocities are, and number 2, how long it's going to take each of those to occur. So we got the general shape of the graph. Now let's actually figure out what the velocities are. And I'm just going to erase some stuff. Okay, so notice that the first part of the blue wave, make this a little bit clearer, this part of the blue wave is going to cause the string to move up 0.5 centimeter. That distance right there is going to be 0.5 centimeter in a time of 1 second. So that's 2 boxes, and so since it tells us each line is 0.5 second, 2 lines would be 1 second. And so if we go velocity is displacement over time, if it moves up 0.5 centimeter in 1 second, then that gives us a velocity of 1/2 centimeter per second. And so since that's point P is right there, that's going to happen right as we start our stopwatch here, our very first velocity is going to be 1/2 centimeter per second. And then since it's going to take 1 second for us to get to the peak of that wave, I'm going to go ahead and sketch that line to be exactly 1 second long. When we get to the back part of the wave, so now I'm referring to this part, now our string is going to move down 1/2 centimeter. So I'm going to change my velocity equation and make that negative 1/2 centimeter per second. It's still going to be 1 second because 2 boxes is still 1 second. And so 1/2 centimeter over 1 second gives us negative 1/2 centimeter per second. So for the next 1 second, I'm going to graph a velocity of minus 1/2 centimeter per second. And so thus far, as the first wave moves through, it takes 2 seconds for it to go from the front edge being at point P until the back edge is at point P. Then we're going to be at 0 because there won't be a wave after that. And so you may start out part of a line at 0. Realize though that as the blue wave moves to the right, this red wave is moving to the left. It's not just standing still. So in that same 2 seconds, the front edge of the red wave has moved forward 1, 2, 3, 4 boxes. 4 seconds it's moved forward. So really, kind of backtracking a little bit, that as soon as the blue wave finishes moving through point P, the red wave is going to reach point P. And so it's not going to go to 0. We're immediately going to go back to some positive velocity. And again, I'm not sure exactly what that positive velocity is. We actually need to compute it. Let's do it the same way that we just did. So notice that the amplitude of the red wave is again 1.5 centimeters. So 3/2 centimeters. And it's going to go up over a time of 1 second. And so the velocity would be 3/2 centimeters in 1 second. This is difficult math. That would be 3/2 centimeters per second. And so my line's going to be there at 1.5 centimeters per second. Again, it's going to take exactly 1 second, right there, for it to get to its peak. And so we're going to be at a velocity of 1.5 centimeters per second for 1 second. And then the same kind of thing is going to happen on the downward slope. It's going to go back to 0. And so change that to -3/2. So -3/2 centimeters per second. And so graph a flat line for 1 second at -3/2 centimeters per second. After that, both the waves will have moved through. There's nothing else on the string to cause the string to be displaced. And so for the rest of eternity, that velocity is going to go back to 0. So in working these, I recommend you do the same thing. Do the example, check your key, or check your answer with my key, see if you've done it right before moving on to the next one. As always, if you're stuck and you can't figure something out, please come in and see me and we can assist you. And as always, ta-ta.